Hare Krishna students. So this is a very wonderful video. In this video we will calculate the resistance between this point A and this point B. You must have seen this problem at many places. This is a very famous problem. This is a cube and the sides of this cube have the same resistance everywhere. So one of the side, it's one of its point, its name is not given, so I think I should give it. Let us say this is H. So if we will see, then let us calculate the resistance between point A and point B. These are diagonally opposite points. So in this video I will teach you this problem, I think with the two methods I should teach, so that we can have more understanding of different concepts in the same problem. Let us say the first method we will apply here, that is, let us solve it with symmetry. Fine. So how this symmetry works? See here. If you see that when the current reaches at point A, then the current will see three identical sides. Which are three identicals? A to C, A to F, and A to H. Why these all are identicals? Because if you see that ultimately the current has to reach at point B. So the current sees that if it goes from side A, C, D, B, oh, this also A, C, E, B, ultimately it has to travel through three wires. If you, it sees that on the whole the same A to F, F to D, then again B, A to F, F to G, then again B. Here also it has to travel through three wires, A to H, H to E, E to B, then A to H, H to G, G to B. Means ultimately these all three sides are symmetrical. So basically what happens is that this current gets distributed into two parts. I by 3 parts, sorry, I by 3, I by 3, and in this resistance also I by 3. Fine. Now this current, when it reaches at point C, it sees there are two paths again, C to D or C to E, and it has to reach at point B. So again it sees that C to E and E to B, again two wires it has to move, and if on this side also it has to move two wires, C to D and D to B. So again what current does is that it breaks into two parts. This becomes I by 6 and this again becomes I by 6. And when it reaches here, let us see how it works. See it nicely. This is a very important problem. Now this point B, when the current from point A had entered, it has gone in all the three symmetric sides identical, I by 3, I by 3 and I by 3. At point B also, this current I is coming out, and point B will see that all these three sides are symmetrical for this also, B to G, B to E and B to D. So it will say that when the current I has to come out here, then it should come out with all the three identical sides as same. You're understanding what I'm telling? This is identical, this is identical, this is identical. So what it will demand? It will demand that the current should be I by 3 on this side, it should be I by 3 on this side, and it should be I by 3 on this side. And we can see clearly that nearly our problem is done, because we have got current in all the wires come on to this side. This I by 3 came here, two parts just got distributed. This part it got how much? I by 6 because of symmetry. This again I by 6. And if we see this current came to this point, this became I by 6, and on this side again it became I by 6. So we can see clearly here that we have got nearly current in all the wires. This was I by 6, and we can see here at point D, I by 6 came from this side, I by 6 came from this side, and I by 3 went. So this is perfect. So now how we get the resistance of this circuit? What we do is that we connect a battery here. Fine. And what this battery is telling us that key, we have to calculate the resistance of this between A and B point, correct? So what we will say that from the battery I current had gone and the voltage of the battery was V. Fine. And if we want to calculate the equivalent, then the equivalent circuit can be drawn like this. R equivalent, here it will become V, this became V, and the same I current should flow. So if we see here, then the equation will return like this: V is equals to I into R equivalent. So we thought, let us write the equation of this circuit also in the same format. And whatever we will get as V is equals to I in V is equals to I into whatever we will get here, that will be counted as R equivalent. So we thought of writing in this. So what we did, we wrote Kirchhoff's voltage law. For Kirchhoff's voltage law, let us say we started from point this. So whenever we started from point this, we went one step on this side, then it became plus V. Ultimately, we have to go in a loop. Okay? What Kirchhoff's loop law tells? Kirchhoff's loop law tells that you have to move in a loop, and in a loop that the net voltage drop should be how much? Zero. So we'll move like this. We'll move like this, and ultimately we'll come to here. So we started from here, we said that it's plus V, then we went this side, no resistance, no resistance, then we thought we'll go through this way. So when we go through this way, let this resistance is our R. So how much voltage drop? Minus I by 3 into R, because you are moving in the direction of current, and in the direction of current when you are moving, resistance is R and current is I by 3. Then you came to point H, then from point H you move to G. In this, what is the current? Minus I by 6R, and then minus I by 3R. Ultimately it became, from here, then we came here, minus I by 3R, and then again we came at the same point, and it became how much? 0, because net voltage drop is 0. So if we'll see this, this will become, when we will calculate it, this will become around 5R by 6. So what we can say? We can say that R equivalent will come out in this way as 5R by 6. So students, we have solved this problem of resistor network with help of symmetry. So in the next video, I'll solve the same problem in little different way. So you must watch that video also. Fine. Okay, thank you.